Hi, I'll be presenting our work on first-order function approximation for transfer learning in relational MDPs. This is a joint work with Dr. von Petrick. First, we begin with an overview of our work. We are interested in solving planning problems with first-order structure, which can be represented compactly with relational MDPs. We want to learn a generalized policy which can solve multiple RMDPs of the same domain. We illustrate our motivation with the example problem as shown on the left. A robot is tasked to survey some POIs which are represented by the black diamonds in a grid environment. You can learn a policy which is generated by a linear function approximation of the Q function Q theta. In the ground approximation, the features are the set of state fluents. However, the policy induced is not generalized because the Q function cannot be applied to a different problem. We propose a first-order approximation where the Q function is defined over the lifted state action space S hat and A hat, which are independent of the number of objects in the planning problem. Thus, the Q function is generalized and can be applied in multiple problems of the same domain. Next, we describe the initialization of the set of first-order features for a lifted action A hat. First, we lift the ground features for the ground action of A hat. The ground features are the state fluence and its negation. We replace objects in the features with bound variables if they are in the arguments of the ground action. Otherwise, they are replaced with free variables denoted by the star symbol. We then take the union of these lifted features as the first-order features for A hat. Our features are binary and match the value of 1 if it is true in the state ST. We have to ground the first-order features in order to evaluate if it is true or false in the state. The bound variables are substituted with the objects in the arguments of the ground action, while the free variables can be substituted with any object of the same type. Semantically, a first-order feature is true if there exists a grounding which makes it true. However, this results in the coarse granularity of the first-order approximation, which typically leads to a poor policy. Furthermore, the grounding of first-order features affect the Q values and policy, the weight update, and the online feature discovery. We use IFTT Plus on Jeremy 2013 for feature discovery, where increasingly complex conjunctive features are added to the feature set in order to reduce the approximation error. We propose the use of contextual knowledge to restrict the set of objects which can be used to substitute the free variables. This improves the granularity of our first-order approximation. We introduce two forms of contextual grounding in our paper. First, goal context uses objects in goal fluence to substitute free variables. The goal fluents are state fluents which are determined from the reward function or the definition of a terminal state. These are commonly assumed to be known in PRL problems. In the figure shown, the goal is to survey the POI P2. Applying goal context, we substitute the free variable star POI with the object P2. The second contextual grounding is location context, which considers the current location of the agent. Following the same example, the robot is in position 3. Thus, we substitute the free variable star POS with position 3. Location context is motivated from the observation that in many planning problems, especially problems represented with a first-order structure, the agent can only interact with a subset of objects in its proximity. Due to the increased abstraction, we observe plateaus in the first-order approximation. On the left of the figure, we have the full state description of a planning problem, and on the right, we have the abstracted state action space. With the full state description, we can see that the robot should move to the right to survey P2. However, with the abstracted state action space, since there are no POIs in any of the locations, moving to the left or right will have the same Q values, and we have a plateau in this particular state. We propose to mitigate this issue by considering both first-order and ground approximation in the policy, thereby combining the strengths of both approximation, which is better generalization and finer granularity. Both approximations are trained independently with their own weights, features, and TD targets. We consider two types of policies. First, we consider the sum of the Q values Q sum from both approximations. Second, we consider the Q values from the first-order approximation up to episode E before switching to the ground approximation. The second policy is primarily for transfer learning, where the first-order approximation is transferred and served as an informed exploratory policy to train the ground approximation for the first E episodes. We conducted experiments on 4 domains, 3 of which are the IPPC domains. We measured the performance by the total rewards received in an episode. In the Ablation study, where the baseline is the ground approximation represented by the blue plots, we answered the following questions. First, the first-order approximation can solve the planning problems. Second, if first-order features with free variables are even necessary. Third, if contextual grounding reduces granularity. And lastly, if mixed approximation could outperform the first-order approximation. In general, the results shows that free variables are necessary, and contextual grounding and mixed approximation improve performances. In the next set of experiments, we train a first-order approximation in the small-scale problems, and then transfer them to solve large-scale problems. The baselines are the blue and orange plots for ground and mixed approximation, respectively, without any transfer learning. For the green plots, we use only a transferred first-order approximation with no further training. Therefore, the performance is flat with no further improvements over episodes. The red plots are where we switch from a transferred first-order approximation to a ground approximation at episode 750. We observe a decrease in performance after a switch, indicating that a switch should have been delayed to a later episode, as the ground approximation does not yet yield a sufficiently good policy. The purple blocks are where this switching is not done, and both approximations are considered in every episode. Lastly, the brown plots show that the results for transferred first-order approximation, which continues to be trained in the large-scale problems. This is the most computationally expensive configuration, but yields the best performance in general. In summary, we propose a first-order approximation, illustrate the challenges with increased abstraction, and propose various methods to resolve them. We show empirically that our method could achieve generalization and enable transfer learning. If you'd like to know more about this work, please come to my poster session. Thank you.